Welcome to the micro communication course. We continue here the discussion about the various gun oscillator mode here. So this one is about a transit time domain mode here, and these are the possible gun oscillation modes here. Okay, three possible modes are there. That is for the gun oscillation mode. One is about a transit time domain mode. Second is the delayed domain mode, and the a quenched domain mode. So now here we start a transit time domain mode, and in this transit time domain mode, the oscillation period is equal to the a T0 is equal to tau here. Okay, that is about the oscillation period for this transit time domain mode. And here the current is collected. Okay, current is collected only when the domain arrives at the anode there. And the efficiency of the diode in this mode is very low and is less than the 10% in the transit time domain mode. So now next is about we see that a delayed domain mode. Now in a delayed domain mode, okay, now this one is about a delayed domain mode. Just see first a diagram now, and then we'll see that how that domain grows and all that we'll see. Okay, in generally that we say that a domain grows in a negative resonance region. Okay, so this one for this we're supposed to consider that DC bias. Okay, then we're supposed to consider that threshold voltage is about ETH now. Then we're supposed to consider that yes. Okay, and then we're supposed to draw this. This one is about a voltage here. This one is about a time period T here. Then we say that okay. Now this one. Now here you can see that at this particular point, this one is about a tau here. Okay, this one we say that negative resonance region, and this one is about a domain grows in this negative resonance region, and this one is about a we say that a positive resonance region, and in this domain collapses. Okay, same thing earlier we have seen. Negative resonance region, domain grows, and here we are supposed to consider that a positive resistance region. This one is about a positive resistance region. Okay, so in that case, domain neither goes or nor collapses. So this one is about a positive resistance region, domain collapse, and this one is about a positive resistance. We can say that a positive resistance region in which domain neither grows and nor collapse. Okay, so this one is about a negative resistance region. Okay, this one is about a negative resistance region. Here the domain grows. Now in this case here, in a delayed domain mode, so F0L is in between the 10 to the power 6 centimeter per second to the 10 to the power 7 centimeter per second. Okay, that is about it. And the transit time is supposed to be chosen. In this case, it is greater than this. Okay, so 1 here. And at that particular point, the domain is collected at the anode here, and the field here we supposed to consider E is less than the ETH. This one is about field. E is less than the ETH here. Okay, so that is about what we can say that a delayed domain. Why it is called as a delayed domain here? So means this domain forms only after the field value again rise above the threshold value there. Okay, again rise above the a threshold value there, and that's why. There will be a delay between the capture of the present domain at the anode and the field value. Okay, so this one is about a delay. And this one is about a transit time domain mode. So in this case here, in a delayed domain mode, so F0L is in between the 10 to the power 6 centimeter per second to the 10 to the power 7 centimeter per second. Okay, and that is why there will be a delay between the capture of the present domain at the anode and the formation of the next domain there. Okay, so earlier we say that how the domain form, and that's why it is called as a delayed domain. And here the efficiency of the diode in this mode is about a 20%. In the delayed domain mode, the efficiency is about 20%. And again, this generally this delayed domain mode is again it is called as a inhibit mode. Next, we see that another mode that is called as a quenched domain mode. Another mode is called as a quenched domain mode. Now, in this quenched domain mode, we will see that what will be the values of this quenched domain mode with respect to that F0 into L here. First of all, we're supposed to draw this how this domain grows and how this domain collapses. Okay, so that's this. We first of all we see here. Then this one is about your DC bias. Then we're supposed to consider that ETH here. Then we're supposed to consider that ES here. Okay, and then we're supposed to see that how your domain grows in the given region. Okay, this one it is about the below ES now. Okay, so this one. Here in this one we can say that a domain grows. This one is about a negative resistance region. Here this one is about your domain collapse, and there is a delay. Delay means what? How this delay comes? This one. This one is about it over here. So that's why here this one is the region here. This region here, the domain is not neither growth or nor collapse. This one is about a positive resistance region, and in which that tau value we supposed to consider that here, and that's why it is called as a delayed domain. So, sorry, there is a quench domain. Okay, not a delayed domain. So we supposed to consider that in this a quench domain mode here, F0 into L that will be greater than 2 into 10 to the power 7. And here this one we supposed to see that these are the bias voltage here, and in this particular mode that a bias field drops below the sustaining field. This one bias voltage drop below the sustaining field here. Okay, this one is about the sustaining field, and due to that this particular domain is called as a quantum domain. Now this happen. Okay, this happen in the negative half cycle. This one is about a positive half cycle. This happen in a negative half cycle. And because of this, what happened here? A that collapse of the domain before collection at the anode here. Because of this drop of this bias voltage here, then that collapse of the domain occur before the collecting at the anode there. Again, when the field again rise there above this particular threshold value, then new domain start forming, and then again this process repeats there. And in the quench domain mode here, the oscillation frequency it is determined by the whatever the resonance circuits we are using instead of this a transit time there. So this one is about a transit time is what? This time is what? A new domain start. Okay, this one is about a new. So here below this it drops here. Okay, means drops means what? So then it will be collected at the anode, and then new domain start at that point at this particular transit time. That is about it over here. Okay, so this generally is supposed to be considered that uh, this quench domain there, and that in a quench domain mode the oscillation frequency it is depending upon not on this transit time, it is depending upon that a resonance circuit there, and the efficiency of this diode in this mode in a quench domain mode it is about a 13%, 13%. Efficiency is about a a 13% efficiency there. And in general practical there, gun oscillator to be used in a various configurations. Okay, not only this different mode there, we supposed to be consider that a various configuration is to be used in a gun oscillator there. Okay, so that's why we supposed to consider that how this gun oscillator circuits are there. Just like I'm going to draw one circuit there, equivalent circuit of a gun oscillator in the gun oscillator mode. It has tune circuit there. I'm supposed to draw a smaller one. One is about the inductor here, resistance, then a capacitance here, then a resistance, then a capacitance here. Okay, and here with a parallel capacitor, that is about a CP here. So this one we supposed to consider that circuit here of this, what we can say that equivalent circuit of the gun oscillator in a gun oscillator mode here. Okay, so this one is the equivalent circuit supposed to be considered, and generally we supposed to use the gun diode where we have the high Q is there, or we can say that in a microwave cavities that gun diode is to be used, and that particular cavity it has a high Q value. Okay, so we'll see that how this gun diode will work there. Another mode is about a limited space charge accumulation mode. Limited space charge accumulation mode. Okay, now this one is about a limited space charge accumulation, or we can say that a LSA mode. This is supposed to be called as a LSA mode, or generally that a gun diode is exhibiting in a LSA mode, that is called as a LSA diode. Gun diode exhibit in a LSA mode, it is called as a LSA diode. So what do you mean by this LSA mode here? So in a LSA mode here, that LSA mode defined by F0 into L, this is to be greater than 2 into the 10 to the power centimeter per second here. And ratio of N0 by F0, it is in between that 2 into the power 10 to the 4 to the 2 into the power 10 to the 5. Okay, that is about, and generally it has a, whatever the dope material is used, and that dope, it doesn't have the internal space charge there. And same way it is applied, we supposed to consider that a field, when we apply the field to the LSA mode here. So in this particular LSA mode of operation in this particular device, so what happened that electric field will be uniform there. And again, we say that that electric field, it is proportional to the, that field generated in this particular mode, it is proportional to the whatever the applied electric field there. And this device is also we supposed to be consider that we we have the a drift velocity of this device is depending upon that what will be the current here. So that's why in general a LSA mode here we supposed to be consider that a frequency of oscillation in a LSA mode, it is a very high, and when the domain formation takes place, it will not get a sufficient time to form the a domain here. Okay, so we supposed to draw here how this domain formation takes place now. This one is about your B here, this one is about your T here, and we supposed to consider that DC bias, then ETH now, then we say that a ES here, okay, and then here this one we supposed to consider that we have the okay. So this one is about a ALSA mode, and then sorry, and that is about your toe. That is about a region. So here we supposed to consider that generally we say that for a given any diode here, so accumulation of a charges is takes place near the cathode, and then a domain grows there, and then that domain will move here for further forward there, and then it will reach to the anode there. So that's why we say that because of that domain growth and domain movement here, so that's why this device will work in the a negative resistance region. And again, we supposed to consider that when we supposed to be apply a further bias there for the given particular circuit, again it will start fluctuation, or we can say that it will start the oscillating there. Okay, so we supposed to say that this particular LSA mode of a operation, that gun diode in LSA mode of operation, it is to be called as the LSA diode, and this depending upon this diode will very sensitive when we say that a domain grows there and domain fluctuation. Now this one is about your domain growth region. This is about negative resistance region and domain growth here. And here in this region we supposed to say that a negative resistance region, and after that a domain neither grows or nor collapse there. And this one is about a region here. This one is about a domain collapse, and this one is about a positive resistance region. Okay. So domain collapse means what? It is collected at the anode here. Okay, so that is about, we can say that further it will be collected at the anode there. And generally that LSA mode, that frequency of oscillation, it is not depending upon the transit time. It depending upon that what resonance circuit is supposed to be used there. Okay, so this one is about a LSA. So we supposed to find out that how much is the power output for this LSA mode now. Okay, so we say that, so it is depending upon that P is equal to, that is about the, we say that it is about the conversion efficiency, that DC to RF conversion efficiency, then a capital M, that is about a multiples of operating voltage above the negative resistance threshold. Okay, so we have the multiple there, earlier we say that, and then we supposed to consider that what will be the threshold voltage we are applying, and what will be the a donor concentration there. Okay, then we supposed to consider that E, then we supposed to use that what will be the charge and what will be the average carrier drift velocity there, and then what will be the length of the device and what will be the area of the device. So this one we supposed to calculate that what will be the power output of this LSA diode. Okay, and then equivalent circuit of a Gunn oscillator circuit in a LSA mode there. This one is about LP. Then we have the resistance there. Then we have a capacitance, and then we have the parallel capacitance. That's about a CP. This one is about the equivalent Gunn oscillator circuit in a ALSA mode there. Then another mode, we say that stable amplification mode. Okay. Another mode is called as a stable amplification mode. Okay. So in this stable amplification mode, we supposed to consider that what will be the mobility and the length of the device. That is about 10 to the power 11 per centimeter square to the 10 to the power 12 per centimeter square. And a F0 into L is approximately is equal to 10 to the power 7 centimeter per second. And in this case here, in a stable amplification mode, we say that in this particular situation and such condition that at some particular place, we're supposed to see that a domain will not grow. Okay. And there are some a few carriers, they form the domain within that particular transit time, that is about a 2 here. And that's why the amplification of the signal near the transit time frequency can be happened there. So that's why it is called as a stable amplification mode. Another mode is there, a bias circuit oscillation mode. Bias circuit oscillation mode here. So in a bias circuit oscillation mode here, so that oscillation occurs at some particular value of the bias there. So generally we say that a gun diode is work at some particular bias value, and or we can say that at some particular threshold value, and then from that particular threshold value, then gun oscillation will start there. And then means, because at some particular means, we say that here generally current increases there, that is about some particular threshold value, then current starts drop there. So it means at this particular point, then gun oscillation start, and then we further bias, so gun oscillation start and current start decreasing there. Okay, this is about what you can say that a bias circuit oscillation. So at what particular bias your gun diode will exhibit, and then it will start oscillating there. So generally in the considering that at what value of the bias, in that case we supposed to be say that a bias circuit oscillation mode, your operating frequency ranges from the 1 kilohertz to 100 megahertz. Okay, that is about a oscillation frequency mode. And that oscillation frequency mode, if it is here, we see that it is about very small. That is about 1 kilohertz to 100 megahertz. And that's why we're supposed to use a gun diode with respect to with some cavity, so that that cavity frequency that with a high cavity, and cavity has some resonant frequency, and then a gun diode will operate at that particular micro frequency, okay, of that cavity. Okay, so that's why is we supposed to be use a various mode, and when we supposed to be consider that various mode, we supposed to find out that in which mode we will get that a micro frequency there. So another case is about how to construct the gun diode there. So in which here this one is about a metal contact. Okay, that is about we can say a anode here, and then we have the different substrate, and this one is about a n plus 1 substrate. Then here we have the active end here. I'm just going to write down outside now. Okay, that only n now. Okay, and then this one is about a n plus. This one is about a metal contact for what? A cathode. This one is about a metal contact. This one we say a anode, and this one we supposed to say a cathode now. This metal contact for the cathode there. And a equivalent circuit here. Generally, we say that for this given particular gun diode, the equivalent circuit has a resistance Rs, then LP here, and then we're supposed to consider some impedance and a tank circuit. So this one we supposed to be consider that a equivalent circuit for this. Here we say that junction capacitance and junction resistance. Okay, so metal contact, for the metal contact there will be lead inductance and a resistance. Okay, so likewise, and across that there will be a capacitor, plate capacitor. So this one is about your equivalent circuit of a gun diode here, and how this gun diode will work as an oscillator. Okay, so generally we say that a gun oscillator, it is to be used with a waveguide cavity. So waveguide cavity gun oscillator. We're supposed to draw here a diagram. This one is about your cavity now, and here in between this cavity, small portion is opening here, and through this one is about a waveguide now. Okay, this one is supposed to be considered as a waveguide now, and through this one is about a post here. Okay, this one is supposed to be called as a post now, and then this post is connected to the sorry post length. I just draw it very small now. This one is about a post now, and then at this particular post there is a device, and this one is about your gun diode. Okay, throughout this one is about your waveguide, and then we have the inductive diaphragm. This one is about a inductive diaphragm. Okay, and then along with that, tuning screw is used. That tuning screw is used to form the post. Okay, window, some window or a post there. So that's why that cavity will be changes. Okay, so that is about a tuning screw. Sorry, this one is about a tuning screw now. Okay, this one is about a tuning screw here, and we supposed to be apply a bias to this post now. Okay, so this one we supposed to apply some particular bias voltage. That is about your V here. Okay, now this one is about your a circuit. That is how this a gun device is used. So generally a gun device is to be present in the rectangular waveguide, and this one is about a rectangular cavity. This one is about a rectangular cavity, and this cathode is connected to the cavity. This one for the gun diode, and anode is connected to the post. This one is about a post here, and the resonant frequency of the cavity can be adjusted here with the help of a movable short. So short is here. So this one we have a short here. So we supposed to be increase this okay cavity using this. We need to move this short here. Okay. So then we supposed to move the short at the one end, and again we supposed to consider that there is about a inductive opening. Okay. So we supposed to consider that inductive diaphragm there, and that inductive opening is located in between that waveguide and the cavity there. Again there will be a tuning screw, and that tuning screw is used to provide the fine tuning the for the resonance cavity, so that we supposed to find out that what will be the resonant frequency for this cavity there. So according to that, when we apply some DC bias voltage to this device there, then what happen? Then your diode will work in a LSA mode there, and then it will work as a oscillator. So that's why that's all about. We can say that a gun oscillator there, and in this case here we have the rectangular cavity there, and based on this particular rectangular cavity, your gun diode will exhibit there. And for the LSA mode here, if you draw a equivalent circuit for this diode here, so in this case, we're supposed to say that this one is about a LP. Okay, then we have the Rj now. Then along with that, there will be a junction capacitance, and this one will be a CPL. Okay, this one is about a ACJ. Now this Rj is nothing but the negative resistance. Generally, it is for this given particular diode because it is exhibiting in a negative resistance region. So that's why it is about a negative resistance. Okay, we say that is about a Rj here. And a capacitance for this that is about a Cj here. Okay, negative resistance Rj and capacitance Cj here. And we have the for a given particular circuit. So we supposed to consider that given particular region that LP and CP, it is depending upon that what will be the cavity of the your particular uh, device, okay, or a circuit. Okay, that's all about your a gun diode. So, we supposed to see that a various we have seen the various mode there, and we have seen that a gun diode as well as the gun diode will exhibit in a LSA mode that we have seen, or that is LSA mode of operation of a gun diode is called as a LSA diode. So today we have seen the two device that is about a gun diode as well as a LSA diode. So thank you all of you.